Okay, as we continue to talk about electrical safety, we're going to move on to a couple of devices that can be used for the purpose of keeping electrical circuits and people safe from harm, because electricity can be very dangerous and it can be deadly. So what we have here in this video are two things. They're called fuses and circuit breakers, or sometimes people just call them breakers. In this image here we have some fuses, and as you can tell they come in various shapes, sizes, and structures. And then here we have a circuit breaker. They also come in various shapes, sizes, and structures, but they all have a switch like this. At least one. This one kind of has two. In any case, that's what we're looking at. We're going to get into a little bit more detail, obviously. But you can see that there's a whole bunch of different shapes and sizes and so on to these different devices. Alright, we're going to go with the most basic shape of a fuse. This is the kind of thing that you might find in AVR, an automatic voltage regulator. They have a fuse very similar to this, at least the ones that I've seen. Or a power supply, like say a direct current power supply or something like that, that we might use in a lab. Those are going to have a fuse probably that looks like this. It's a glass case. Inside there it's vacuumed out, so there's no air. The end caps are conductive, and then in the middle there is a filament, or what you would call a thin wire. So that wire completes the circuit from one end of the fuse to the other. And then the ends of the fuse hook into your larger circuit, and that it just operates like normal, just as though it were a wire in the circuit. But this wire is special because it's designed to fail or melt if the current in the circuit rises above a certain value. That value is the rating of the fuse rating. So you can't see what the rating is on either of these fuses. It's always printed, etched into the metal on one end, and you can see that it is here on this fuse, but it's hard to tell what it says there. It might say 25 volts. It definitely has a 5. It could be 125 volts. That would be my guess, perhaps, because that would be a good fuse to have in the US, 125 volts. The voltage is supposed to be 110, so if it's above 125, it's definitely too high. So that would be my guess on that one. And then it'll also have a rating for how many amps it's allowed to take. So if either the voltage rating or the amp rating is exceeded in the circuit because of something going wrong, like say there's a short circuit or other kind of fault in your electrical device, then this fuse will break. And hopefully, ideally, the fuse will be the first thing to break, and all of the rest of the electronics will be kept safe from harm, and as well anybody who's touching the device after it has failed will also be kept safe from harm. So that's the idea of a fuse. The fuse breaks so that nothing else breaks. Alright, so here is a symbol, the electrical symbol that we would use if we were putting a fuse into a circuit diagram. So it's just basically, it's a resistor essentially, but with a line through the middle. So that's why it's important when you're drawing your resistors to not put a line through the middle, because otherwise you've drawn a fuse. Alright, so just a quick comment about where you put a fuse if you're designing a circuit, say for a toaster oven. If this toaster oven developed an electrical fault such that it is drawing too much current or too much voltage, and that's going to be dangerous for its internal stuff or whatever, or for the person who might be touching it, who could then receive electric shock because of the fault, you need to put a fuse. Usually you try to put it in the plug if you can, so inside the plug assembly, or at the very least you would put it at the entrance to the casing, where the wire meets the casing. Now you might remember that we talked about inside of the wiring there are two wires. One is neutral and one is live. So I'm just going to label them L for live and N for neutral. And then this is going to go to the toaster. All right, so which wire do we put the fuse onto? Do we put the fuse on the live wire, or do we put it on the neutral wire? The answer is we put the fuse on the live wire, and the reason for that is that we need to cut off the power supply as soon as possible to the device. So if you think of the live wire, you want the fuse as close as possible to the wall, right? As close as possible to the wall, so it's ideal if it's inside the plug. But if you can't put it inside the plug, then you want it as close to the wall as possible, not in the plug. So you definitely need to put it in the pathway of the live wire. So there's a fuse attached to the live wire as we've drawn it there. This basically means that if the fuse fails, the power supply is cut off from that point onwards. No more power. All right, no more electricity after the fuse. So all of this down here, all of this will have no electricity running through it at all. Now, if you were to put the fuse over here in the neutral wire instead of the live wire, it would still fail if there was a fault in the toaster. The fuse would still fail, it would burn out. But here's the problem. Electricity would still be flowing through the live wire up into the toaster and back until it got to the neutral wire. This would still be potentially energized. I suppose it wouldn't actually be flowing now, but it would still be linked, right? Potentially. If somebody comes along and touches the toaster, and let's say that it's developed a fault, a short circuit, so that the casing is now energized, somebody comes along and touches it, suddenly, because the live wire is still active, and now somebody has come over and touched the wire, say right there, now they're going to be connected to the ground, little ground symbol, and that's going to complete a circuit. So electricity will flow through the live wire, through the toaster, through the person, bam, to the ground, and they're going to get electric shock big time. So if you do not put the fuse in the live wire, then a faulty device that has blown its fuse may still be dangerous to somebody who touches it. Right? If the fuse was over here in the neutral wire instead of being in the live wire. Right? That's a little bit complicated. I hope that was clear. But basically, even if you didn't understand the explanation, just understand that you have to put the fuse in the live wire, not the neutral wire. All right? Because otherwise it can be dangerous to people who come along and touch the device later. Okay, circuit breaker. Circuit breaker serves the same exact purpose as a fuse. It will break the circuit if there's too much current or too much voltage. Basically, this switch will flip and the circuit will get broken. The difference between a circuit breaker and a fuse is that a circuit breaker is an electromagnetic device and it can be reset. So if a circuit breaker flips, then all you need to do is fix whatever it was that caused the circuit breaker to flip and then turn it back on again, and you're all set. You don't have to buy a new fuse, which is nice. Now here's a diagram of how a circuit breaker works. This is a simplified diagram, but it has all the basic parts. You've got a power supply. Of course, that would be like usually a wall socket. Or actually, in this case, not a wall socket, but your actual electrical wiring is going to be hooked into the power supply that's coming into your house. That's going to be hooked up to an electromagnet and coiled, basically coiled there, come out here. This is going to be a soft iron core. So that's the electromagnet part of the relay. Sorry, not relay, circuit breaker. The rest of this goes to the circuit in the house. Here you have a switch, which is spring-loaded and connected to this green apparatus here. And then you've got this cylinder, which is also spring-loaded, all right, and it's also iron. So this can be attracted over to that electromagnet. Now, normally, this spring-loaded cylinder is held away from the electromagnet. The electromagnet is energized up to a certain point by the current that is flowing through it. But remember, just like a fuse has a certain rating, a circuit breaker also has a certain rating, and it's going to be based on how strong this spring is. So the stronger the spring, the higher the rating of the circuit breaker. But if the rating is exceeded by the current that's flowing through this electromagnet, you might remember the amount of current flowing through an electromagnet is related to the strength of the magnet. So more current means a stronger magnet. If the current gets too high, this magnet will now be strong enough to attract this cylinder, and the cylinder will move that way. Just like that. Alright? So the cylinder now jumps over. Alright? And remember, this switch is spring-loaded, so it's pushing up. It's pushing up, but it's pushing against the cylinder, so the cylinder holds it down in place. If the cylinder is removed, the switch pops up, and then this switch here becomes open instead of closed. So let's look at how that looks after it's been tripped. Okay, same basic idea, but now the cylinder has been attracted to the electromagnet. This whole switch apparatus has popped up because it's spring-loaded. It's opened the switch, current has stopped, and the cylinder is holding this thing open, right? So this thing has popped open, it's sprung open, it's not going to go back down, it's not going to close again. Everything is all locked in this situation, right? So until somebody comes along and flips the switch, which pushes this guy back down, and then this will slide back into place. Until that all happens, this is stuck like this. The circuit is open and no current is flowing. So that gives the homeowner time to go find out what the problem was and fix it, and then reset the circuit breaker. So again, the advantage of a circuit breaker is that it is resettable and you don't have to buy a new one. The advantage of a fuse is that a fuse tends to work faster than a circuit breaker. So sometimes a circuit breaker is not fast enough to prevent damage. The other thing is a circuit breaker is rather large. So you can't really put a circuit breaker in a small device, but you can put a fuse in a small device. So that's a little bit of the give and take of the two different ways of doing things. And that is an explanation of circuit breakers and fuses. They're designed to protect electrical devices and also to protect people if the devices develop an electrical fault that might be dangerous to somebody who touches them. All right? So the fuse or the circuit breaker will cut the electrical signal, it'll cut the flow of current, and protect everything else, hopefully. So there you go. That is our topic of circuit breakers and fuses and how they work. Thanks for watching this video, and I'll see you in the next one.